All right, we want to start getting into the real chat about energy. So in physics, we have talked so far about kinematics, which is studying motion. We've actually talked, and I haven't used this term, we've talked about statics a little bit, which is the study of forces, but you're looking at them in equilibrium. We kind of touched on that. And then we also studied dynamics, which is that case of non-zero forces and the motion that results from them. So, forces causing some sort of acceleration. So all of this together, this branch of physics is actually what we refer to as classical mechanics. And any physicist is going to have a very good, solid foundation in classical mechanics. It's essentially the basis for a lot of physics until you get to quantum mechanics. Now, all the forms of energy that we've kind of looked at previously, the gravitational potential energy, elastic potential energy, and the kinetic energy, these all form what we refer to as mechanical energy. So mechanical energy in Science 10, you probably referred to it as the total energy. That's fine too. But basically, if we want to calculate mechanical energy, all we're doing is we're adding up the total kinetic energy of the system and the total potential energy of the system. And that potential energy could take form of gravitational potential, or it could take form of elastic. It could be both, it could be none. It depends on what's going on. The only thing we have to watch out for mechanical energy, because potential energy on its own, not the change in potential, is referenced relative to some point, mechanical energy is also going to be relative to some point. So, I might say this system has 200 joules of mechanical energy relative to the ground, or 500 joules relative to the ceiling. We have to be specific with our reference point. Now, the key for us, at least for a big chunk of Physics 20, we will assume that the mechanical energy of a system does not change. This is going to form the basis of the law of conservation of energy, which we're going to talk about a little bit later. But let's look at this. So we have a 200 kilogram cannonball. It's going to reach a maximum height of 35 meters above the ground when shot vertically in the air. So we'd like to find the cannonball speed at 13.7 meters above the ground. So the first thing is, let's look at maximum height. Now, at maximum height, we know an object's velocity is going to be 0. That's just kind of what we've talked about. The object's going to rise, at its highest point it's going to temporarily stop, v equals 0, and then it'll fall back down to Earth. So if I look at the mechanical energy at any point is going to be the potential energy plus the kinetic energy. Well, if we're at the maximum height, we don't have to consider kinetic energy. That term is gone, so we don't actually have to worry too much about it. What this is telling us is that at maximum height, the mechanical energy is going to come from potential energy, which is just going to be mgh. So we know the mass is 200 kilograms for the cannonball. We know gravity is 9.81 meters per second squared, and we know it's 35 meters above the ground. Now, what this is going to do is this is going to give us our total energy at this point. And I'm not going to worry about sig digs for now. So what I'm getting here is I'm getting the mechanical energy at the highest point is 68,670 joules. This does not change. What this means is that no matter where we are in the system, the total of EP plus EK is always going to equal this number. Now, the individual values of EP and EK may change, but they always have to add up to this number. So what we kind of have here, and I'm just going to make this little sketch, like if this is my total energy, this has to be made up of kinetic and potential. Well, at the highest point, this mechanical energy is made up of no part kinetic, but it's made up of all potential. So what we would say is no matter what, this value stays constant. These are free to change such that they both add up to this value. Now, we know the total mechanical energy of the system. That number is not going to change. So we'd like to find the speed at 13.7 meters above the ground. So we know that the mechanical energy is just equal to the potential plus the kinetic. If we're looking for speed, let's at least determine the kinetic energy. So I know that kinetic energy is going to be this mechanical minus this potential, or this mechanical minus mgh. So we have found EM already. We know that value is not changing, and then we can determine the potential energy at this point above the ground. So our total mechanical energy is going to be that 68,670 joules. We're going to take off the mass of that cannonball times 9.81 meters per second squared, and then we're going to take off that height of 13.7 meters. So what this is going to do is this is going to give us our contribution to kinetic energy at this point. So at this point, the kinetic energy's contribution, it's going to be about 41,790 joules. So what does that really mean? Well, what that means is at this point, when we're 13.7 meters above the ground, 41,791 joules of the mechanical energy is in the form of kinetic energy. The remaining 26,879 joules, that's in the form of potential energy. So the values of EK and EP are changing throughout the motion of this object, but their total is not changing. So this EM is not changing. What we kind of have at this point, so again, if this is my total mechanical energy, which is still not changing, this time, however, what we have is we have this contribution from the kinetic, and then we have this contribution from the potential. So these two pieces are going to give me that. What we're seeing as we move along here is we're seeing that the potential energy is decreasing, but that's coming at a cost of kinetic energy. Or sorry, we're going to see that kinetic energy is increasing, and that's coming at a cost of potential energy. So EP is going down, EK is going up. And this relates to the whole idea of conservation of energy. You can't get energy from nowhere. It has to be accounted for. So we know the kinetic energy. So we also know that EK is 1/2 mv squared, and we've done this rearrangement before. So we know that the speed is going to be this 2 EK over m. So we're going to have this 2, and then we have our kinetic energy. And then we're going to divide that by the mass of 200 kilos. So what are we going to get for a speed here? So we're going to do that times that divided by 200 square rooted. So we're going to get about 20.4 meters per second. So what this is telling us here is that for this cannonball, if it's shot and we know its mechanical energy at maximum height, based on the information we know, when it's 13.7 meters above the ground, it's going to be traveling at 20.4 meters per second, and it's going to continue to pick up speed until it hits the ground.